So the midterm examination results have been posted on Canvas. You can check. Most of the students can get a 70 or 80. There is only one full score, 100. Can you write down extra credit for the attendance today? Yes, yes. I'm sorry, I have no blank paper, but you can use that. So today we will talk about memory hierarchy and cache. So you can see that there is a speed gap or latency gap between the CPU. CPU double every maybe 3 years or 2 years. But you can see that the memory so there is a gap. This gap doesn't hurt if you have a computing intensive workload, because your workload mainly are running. And that hurt the workload which heavily use the memory. Because nowadays we have a lot of big data applications. So this is the normal case for today's benchmark speed. Then the memory hierarchy becomes more and more important. So this is the memory hierarchy. There are multiple layers. In the top layer, of course, is registers. We introduced the pipeline register in previous lectures. So the registers will be very fast. If your CPU can run at 4 gigahertz, then the is in 0.25 nanosecond. At the bottom of the hierarchy, so it's the slowest component in the memory hierarchy, but the capacity SSD flash. Nowadays on your mobile phone, of course, but in the iPhone system, because this can provide much dense storage. So exactly, we have 2 more. The first one is a cache. The second one is memory. Cache is fabricated on the CPU die, but the memory has its own die. So you can see that at the top layers, it's faster, but it's more expensive. In the bottom layers, very slow and cheaper. When you write a application or run your application on CPU form, and how to do scheduling how to do replacement so that you can are very important. So today we will talk about cache. The so-called SRAM is a static memory. So the cache is managed by the hardware, which means that you cannot write application to configure the cache. The cache behavior is decided by the CPU itself. So we have actually divide blocks. Each block costs only several bytes, for example, 22 bytes. And this 22 bytes is one block, which means that it's one cache line. Each time, and store this cache line into the cache. When you write a loop, for example, for I equals from 0 to n, when you write some for loop like this, when you have a array inside this loop, you actually call it spatial locality. The spatial locality means when you access one element, potentially you will access its neighboring elements. And the temporal locality means it's very likely you have another and you will access this element in a very short time. So in order to improve the heat rate of the cache, we need to improve the locality, including the spatial locality and the temporal locality. So here are some definitions. The first one is a cache line block. The cache line is the minimum size we read from the granularity size we read from DRAM cache. So each time we read 22 bytes or 64 bytes. Frame means the physical location in the cache which can store the cache line. After we read a cache line from here, we will store the data in the cache. The maximum capacity of your cache maybe only can store, let's say, 4 cache lines. And each cache line here, each frame, each cache line, each 32-bit here is a frame. You only have 4 frames, and this 4 frames can store 4 cache lines. If you can find your data, the data you want to read in the cache, this means heat. Otherwise, if you cannot find it, it's called a miss. So miss ratio means you read about 100 times. You try to find your data 100 times. How many times you can actually find your data? And heat time means after you find out you have a heat, how many cycles it takes for you to read your data, actual data from the cache to the CPU. Miss penalty means if you have a miss and how much how many cycles you needed to take to read your data from the DRAM to the cache. So the latency from here to here is called a penalty, means penalty. And the latency from here to here called a peak time. Then we will have one example. So here each frame and each cache line is 8 bytes. And these are the 8 bytes. When we first issue the first request, of course, it will have a miss. Why? Because you have an empty cache, or called cold cache. And then you fetch the first line from the memory to the cache. When you try to read the second line, because each line is 8 bytes, so from 1, 0, 0, 0 to 1, 7, these 8 bytes are actually in one cache line. So when you read this line, you actually have this address. So for the second access, you can actually find this data in the cache. When you read the third line, it will have a miss. Because the maximum value for this line is 130. This range does not include this line. So you need to read this line from the DRAM. After you read this value, you have a range from 1 to 1. And then we read the next line. Unfortunately, it's a miss because for this one, the maximum value is and then the next line will be this line. The rank here, he moves this line. And then for the last line, it's okay, because the last line also. So from this line to this line, this is a spatial location. Because this line is actually it's just like the New York side, A0 and then A1. From this line to this temporal location, which means that you, in a very short time, you can read these 2 times. Because we have 6 reads, and 3 of them are heat. So the miss rate is at 50%. And of course, you want to improve. You want to improve. so that you can read more data from the cache. The cache is faster than the memory. So here I will introduce a equation to compute the latency, average access latency. So assume the cache heap will take 10 cycles, and the memory access will take 100 cycles. What's the value of the average latency? So if you miss rate is 50%. 50% means you read the cache 50% for 50% access, and read the memory for the other 50%, and then sum them together. The value here indicates the average latency. So when you have 10% each process, 90% you read your data from the cache, and 10% you read your data from. This is the second line. And if the miss rate is only 1%, for 1% of possibility, you read your data from, then 99% you read the data from a cache. So you can see that by decreasing the miss rate, you reduce the average access latency. Because the cache is very important. Nowadays, you have a 3-level cache, or 2-level cache, or even 4-level cache. So sometimes we have an L2 cache. So how we will change this equation if we have the L2 cache? The L2 compared to the L1 cache, the L2 cache is larger, but also slower. The L2 cache generally takes 20 cycles. So if the miss rate is at 80%, and the miss rate in L2 is 40%, what's the average access latency? So if the miss rate in L1 is 20%, then the L1 can handle 80% access. Then the first part is that what will happen for 80% the memory access will use the latency of L1, which is 5. 20% will go to L2 and memory. Among this 20%, 40 will actually happen in the L2. I'm sorry, 60 will happen in the miss rate is 40%, and the other 40 will go to the DRAM. This is the latency of L2. This is the latency of DRAM. And you can add these 3 parts. You can sum these 3 parts together. Because the miss rate of L1 is 20%. So for 20%, for this 20%, you need to access L2 and the DRAM. And then 60%, you can find your data in L2. 40% you need to go to the main memory. And then you can sum these three items together. So you can see that when you add a L2 cache, you can significantly reduce the access latency. Here, you need to reduce the access miss rate to 1%. This is a very difficult. But when you have a L2, even the L1 cache miss rate is very high, you can still achieve a very good access latency. That's the reason why we have a 3-level or even 4-level cache. Particularly nowadays, you have a many cores, or at least 2 cores, 4 cores, or 8 cores. And each single core has their own L1 cache and L2 cache. And the 8 core or 4 core may share the same L3 cache. And they share the same main memory system. The so-called shared or unified is different from split or private cache. Particularly when you run different workloads on the different cores. If you have a very memory intensive workload, require a very large cache, because the L1 and the L2 some core may not be able to use all the caches, all the L1, L2. It cannot borrow the available space to the other core, which require larger cache. But they can, do that borrowing stuff in L3. Because L3 is shared. So this is the case for the multi-core. Each core has their own L1 and L2, but they share the same L3 cache. And you can see that the cache area actually very large on the modern chip. Even even in the area of core, even in this area, you still have a significant area for the L1 cache and the L2 cache. So you can see that the structure of the memory of the Astron by the array structure. And here you also have some array structure. So you can see that the Astron approximately may cost 40% area in the CPU. Then I will introduce what's the Astron. So one component, the core of Astron, just include just two inverters. The output of the first inverter, the output of the first inverter of the second, and the output of the second inverter connected to the input of the first inverter. Assume that here you have zero, and this zero, because this is the one, and this one, because the input is one. So somehow you achieve a very stable state. So if you have a one, because this is also a stable state. No matter you have a 1 or 0 in this, in the chain of this two inverters. So this is the core of that. You also have two transistors here to serve as the access transistor. And these are sensors. Each can actually sense the data from, sense 1 or 0 from the core. When you close the value, assume that the D stored in this memory, and you will have it can also be detected by the sensor. So the cell after cell only. Because each inverter includes two transistors, you draw them. We draw the, the layout of the PMOS, CMOS here, and this is the. This is the input, and this is the output. So the inverter contains only one PMOS and one NMOS. You have two. So totally, you have 6 transistors, and this is so-called 60 as well. One SRAM cell will cost you 6 transistors. So the overhead here is very large. That's the reason why you can only have a limited capacity of SRAM on a CPU. So when you try to write this down, you also inject the current through the sensor amplifier. And inject to change the state of the cell. And of course, we have multiple cells here. And these cells share the same line. And that line can control the access transistor for all the cells shared by this line, shared on a sharing. This is the sharing. And this line connects all the all cells, all these cells. So when I become each section are PMOS, so you can see that these transistors are PMOS. When I apply a 1 on the PMOS, it will be closed. So when I apply a 1 to this one, vertical line. So this means that it's possible for me because these cells share the same horizontal line. This is the, this is a case we want to achieve in the cache. Why? Because each time we read one cache line, one cache line includes multiple bytes. So we call the vertical line. Because each time we may need to read one word or multiple words. And the vertical line will actually help you through the vertical line, yes. And the vertical line are called bit lines because each vertical line will give you 1 bit. When you have multiple word lines, so you can see that in this array, multiple cells share the same vertical line, multiple cells share the same vertical line. So in order to read this array, we need to first select a word line. By selecting this word line, we set a 1 on this line. If this line has a 1, only this row of the cell actually connected to the word. And then you can read. Can you enable 2 word lines? No. Each time only 1 row can use the vertical line. So by the SRAM arrays, we can achieve the implement. So the general structure of the cache includes the tag array and the data array. So you can see that we have 2 arrays here. Data. Besides these 2, we also have several things in the tag to indicate state of this cache line. The state bit may indicate whether this piece of data is modified by another call, whether this is valid value or not. If someone changes this value, this piece of data will be invalidated. Again, when we send a request, when we send a request to the cache, this is the address we want to read. For example, this is the address we want to read. So how many bits are there in this address? So how many bits this address takes? This address is a 64-bit address. Why? Because your machine is a 64-bit. That's the reason why each time you can send out a 64-bit address. The meaning of this request means we want to read the data stored in this address. We want to read that byte data stored in this address. So you can see that each time you can send out a 64-bit address. This is the hex format. So each bit here, each digit here indicates 4 bits. Because the address is a 64-bit, each digit here is a 4 bit. We have 16. And these 16 digits or 64-bit specifies 1 byte in the number. Remember, when we do the example of the cache, each time we read a cache line. The cache line means each time we read a 32 byte. So when I sign out this program, it will read it will read 32 byte. And the 32 byte will share the same value on the most significant bit to these bits. So for these 32 bytes, these parts are the same. Only the several least significant bits are changed here. So that's the reason why we to serve as the block offset. The block offset indicate this is a cache line. And all the other bits here indicate the tag. The tag means when I send out this address, I need to check these bits whether they are the same as my request. If they are the same, okay, this is the line I'm looking for. Otherwise, this is not the line I'm looking for. So these bits will be stored in the tag. In the tag arrays. And the data stored in this address will be stored in the data. For example, this byte may be a 1. So when you try to read the cache, you first issue to the cache and compare the text means the text will check whether these bits equals to your request. If they are equal, then you find your data here. The next step is when you find your data, it's key. If you are 1. So eventually, your cache will be full. And when you find out that you have a miss, what will happen? You have no free available space in the cache. When you find a miss, you have to kick out some data from your cache so that you can make some room for the new data. That's so-called a replacement. There are several reasons for the replacement. The first one is compulsory. Means you never read that piece of data before. This is a totally new data. And this is the first time you actually read that data. And of course, you will have a miss. The second one is the capacity. You try to sequentially access maybe 1 megabyte data, but your cache is only 256 kilobytes. Then it's impossible for you to cache 1 megabyte. You have to, frequently have a miss in this case. And the other two are conflict and coherence. This is related to the Mohico. They are not a compulsory or capacity problem. So this figure indicates the relationship between the hit rate and the capacity of the cache. When you try to increase the capacity of the cache, you will have a higher hit rate until you reach some sweet point. When you further increase the capacity beyond this point, the hit rate may not significantly improve. But again, each cell costs 6 transistors. So the overhead of increasing capacity is actually very large. Particularly when you consider you have some sweet point here. It's not a good idea to increase the capacity beyond this point. when you increase the cache capacity, the cache becomes larger and larger. Each access happening in the cache will become slower and slower. Because in order to find this word line you want to enable, you need to do a lot of decoding. And you don't want to reduce the cache capacity to some too small value. Otherwise, the hit rate will be very low. We calculate the average access latency. When the hit rate is very low, then the latency will be very low. Another important parameter is the cache line block size. So it can be 62. I'm sorry, 32, 64. Or 16 bytes. The block means each time you read how many data from the DRAM to the cache. So if you read, again, this is the relationship between the hit rate and the block size. If you read too little data, maybe 1 byte only, you cannot capture the so-called spatial locality. Then you will have a miss very soon again. So the hit rate is not high. When you increase the block size, you can catch the you can gain the spatial locality. The hit rate will increase. But it also has some speed point. Beyond this speed point, you just bring more wasted data. The data will be not used by the application to the cache. First, you occupy some space for the useful data because you bring a lot of unused data. Second, you increase the data transfer latency here. So this is not good. You also need to find that speed point. So this is one example of the cache array. You will have a decoder to calculate the decode you also have a max, column max. This decoder also column max. The column max only read this form. You don't have to read all the data on the row. You can select only, a part of the data. So in this example, only read this one. This row. Although you actually enable the AP. Although you enable out. So any question? So today we generally introduce the basic concept of a cache. Why we need a cache? What's the cache for? And how to implement the cache by SRAM. And how to compute the average access latency. So if no question, we can stop. Next lecture, we will continue to work on the cache. Thank you very much.